Okay, so schedule reminder, not that one, this one. Recitation on Monday is the ecosystem of the whole educational programs across the Fab Lab network. And that's going to be the second one in the different location. And we're on to networking. So the assignment is, until now, we've typically had a processor. Today is about multiple processors. So the individual assignment is for you to connect nodes in a network. Group assignment is send a message between projects. And the featured assignment is one of the best versions of that. During the pandemic in Japan, when people were separated for the machine building, rather than a central machine, they made a Japan-wide machine. So this was a part of the musical instrument in each separate location, all coordinated as this distributed musical instrument. So networking. First, why? The obvious reason to do it is because in that case, they were in different sites in Japan. So I'm in Boston and you're in Amsterdam or Alto, just looking at the screen in front of me. So we network because we're not in the same place. But that's only one of the reasons. There's many other good reasons to do it locally in front of you. So one is parallelism. As your project gets more complex and the processor needs to do more things, you can move up to a bigger processor with a multitasking operating system, or you can have separate processors each doing one task. So for the environmental sensor, you can have each sensor has one processor, and then rather than having to read them centrally, each can have associated processing. So you can scale a system by making multiple processors separately instead of multiple cores in one processor. One is modularity. So for the environmental sensing example, you can add one sensor at a time and you don't need to redesign the system. You can debug them separately and you can reconfigure them. And then one is interference. For a system where you, for example, have motors that are high voltage, high current, and then you have, say, microphones that need to listen to noise with very little electrical interference. If you put them all on one circuit board, you have to work hard to prevent power supply ripples from the motors getting into the microphone. But if you pull them apart in separate systems, you can decouple the powering much more cleanly. And so for all of these reasons, within a single system you make, there are many reasons to have multiple processors distributed instead of one big processor centrally. So networking isn't just for distance, it's an important part of system architecture. So first we're going to do wired networks where signals go in wires. Then we're going to do wireless networks for radios. And then after that, I'll talk more generally about principles of networking. So wired networks, inside the processors you're using in the giant data sheets that you were introduced to, a very important component there are multiple different names. So a UART is universal asynchronous receiver transmitter. USART can be synchronous or asynchronous. I'll explain that. These are common terms for the wired interface. SERCOM for ARM processors are flexible, programmable communication processors that can do many different things. In the RP2040s, and I'll show you an interesting example, PIOs are the programmable peripherals. And then bit banging is where you implement the protocols not in a peripheral, but in software. And I'll show you some examples of those. So these are the modules we're going to be using to communicate. So the first example is asynchronous serial. And this is a data sheet that talks about the flavors. We've been, and see, I think I had a picture back here. If we go to embedded communication, yeah, good. So this first and most common asynchronous serial looks like this. This is RS-232, and it's just simply, this is hello world, and it's simply raising a level high and low. And so that's what you've been doing when your processor types a message that goes to your computer. That's so far we've just been doing that where we have the computer, we have your processor, and then we have TX and RX lines between them. But what you can do is you can connect multiple processors. So 422 and 485 are standards for doing that. And this first example I'm going to show you is the simplest one today, but very versatile. It's I'm going to do what's called multi-drop. So here's my host. It transmits out and it receives in. But instead of one thing connected, I'm going to have multiple things connected. Now, they can all listen to the host, but they would fight over this shared line. So one way to do it is, remember, a port can be low, high, or it can be disconnected, meaning it's an input. So what you can do is you can give identities to the nodes, and then you send them messages. So in this example, I've got a series of nodes on a network. Each node gets power, ground, and a shared transmit and receive line. And then in what I'm going to do, I'm talking to each node in turn from the host. And if we look at the code, each node is waiting to get a character in. In the microcode, each node has a hard-coded ID that's different for each one. And then it checks, does the message match my ID? And if it does, it takes over the communication line, sends a message, and then goes back to being an input. And so that's a multi-drop serial bus. It's a bus. It's one line that they're all hanging off of. You need to send IDs to the node, and then you can very quickly talk to each node. So that's our first multiprocessor network. Now, in this code example, if we go back to it, in this example, I'm actually doing the whole thing in software. So this is software to receive a byte, and this is software to send a byte. So in this example, I'm not even using a peripheral. I'm bit banging the whole thing, which means the processor is busy doing it, but the same code works the same on any processor, and you can use any pin to do it. So that's our first example. That's a serial broadcast. Now, this has a limitation, which is you need to tell each node its identity. So in this next example, what I'm going to do, actually, let me show it first, is I've got the host that can transmit and receive. And then I'm going to connect the nodes each to each other. And then in this example, I'm going to do what's called a hop count. And this is a chip that's commonly used for that. This is then what's running inside the NeoPixel. So with the NeoPixel, you're talking to multiple LEDs, but you don't need to know which LED it is. And it's doing a hop count, and here I'm going to do it in software. So here I've got my nodes, and I'm controlling the LEDs individually and collectively, and each node is connected into the next node in the chain. So if we look at the board, here are my LEDs. I've got power, ground, and I've got a receive, transmit. But now there isn't a bus. Receive and transmit goes into one port, and then receive and transmit comes out on another port. And then, oh yeah, the other thing on the board is, actually, that's all I need on that. And so here's what's happening. You count hops. So if the host sends a message, it gets to here. And then there's a counter. And so if it says 0, when it gets to here, you increase the counter to 1. When it gets to here, you increase the counter to 2. And then this node can figure out, which I'll talk about, that it's the end of the chain. And then when it sends the message back, it says how many hops to do. So here we put the ID in the code itself. Here, the ID, we don't have to put in the node. They're all the same. But we're going to count hops. So let's look at the code. So in the code, I'm going to use the serial port. And for the serial port, you need to give it a speed. And there are standard there's standard RS-232 speeds, and modern processors can actually, you can set any speed, but for compatibility, it's good to stick to the standard ones. And so 921/600 is about a megabit, and modern processors are able to do that, which is fairly quick data rate. So I'm setting the data rate. And then the code is pretty simple. Each node has an input port on one side, and it has an output port on the other side. And I'm going to check to see, do I have any communication coming in on my input port? And do I have any communication on my output port? If I'm getting a message on my output port, all I do is I move it from the output to the input. So that's the reverse trip. But if I get a message on the input port, I then have to see what kind of message it is. So this is the important one. This is where we assign addresses. So what I do here is, let's see, let me go back and show you on the schematic again. So we're doing this hop count. I should mention there's one other resistor. On the output port, on the receiver, I've got a resistor pulling it down to ground, this one here. So what that's doing is each of these on the board has a resistor that pulls it down. And that's how you can tell if anybody's connected. When somebody's connected, the line is high. If nobody's connected, the line is low. So in the code, what I do is this message says assign an address. I check to see if I've got anybody connected. And if nobody's connected, the level is low. If somebody's connected, it's high. If somebody is connected, here's where I increase the hop. I take my input, I add 1 to it, and I send it to the output. If nobody's connected, it means I'm the end of the chain, and I turn it around and I send it to the input. So again, in the sequence, the host says, assign your address, and it puts out a counter. The counter increments, and then we get to the end. It says, I'm the end. And then it reports back. There are two, actually in this case, there are 3 nodes in the bus, and it reports that back. So then if we go to the Python code, this is the Python application on the host. And I send out the command to assign the addresses. And then I get back how many nodes there are. And then here I'm sending out a message to hop the LED commands. And so this says what LEDs I want turned on and off. And if we go back to the node code, if it's an LED command, I interpret what is my bit in the command. And then I send the message on to my output. And so if we go back to the video again, so let me stop it here. So I started running, found 3 nodes, means the message went from the host down to the end and back again, and I got my node count. And now I'm going to start sending out messages using the addresses that got assigned by the hop count, and now I can control the LEDs. Okay. So that now I'm talking to multiple processors, and this frees me from having to assign addresses. I can just start connecting them up, and the hop count will find out how many are there, and we'll give them addresses. Okay, so that's hop count. And then I had a project where I needed to do a hybrid where I didn't want to assign addresses, but in the hop count, if you have a long chain of many nodes, it can take a long time to hop a message. And I had a project where I needed to get the messages out more quickly. And so the third version I'm going to show you is a hybrid of these two. And so it's called broad hop. And so the way that one works is I've got a broadcast line that everybody listens to in, but I can locally connect the nodes coming back. So I can send out a broadcast message to assign addresses. This node figures out it's the last node. It sends the message back. Then the host can broadcast a message to all nodes at the same time very quickly, but I can use the reverse path to do the address assignment. So broad hop is a combination of the transmit line I'm routing as a bus, but the receive lines are local to the nodes. And if I do the video, it'll look the same. But now I can talk much more quickly to all of the nodes with this combination of a broadcast out and a hop count back. The broad hop assumes there's always one node in charge. With the hop count, any node can talk to any node. They can pass messages in any direction between any node. With the broad hop version, it's asymmetrical. There's always a host in charge. But if that's the example, for example, talking to a NeoPixel light array, then you can have no addresses, but you can very quickly talk to the nodes. Okay, so that's, this is asynchronous serial. Serial means down the wire, I'm sending high and low levels. And asynchronous means the resting level is high, and at any time I can start sending data. And it's up to the client to be listening and wait to see when that happens. So that's a serial bus. Let's see, let me get back to my notes. So that's a serial bus, simple, straightforward, but needs addresses. Hop count eliminates the addresses, but has some overhead. And broad hop is a combination of broadcast and hop count that has best features of both. And so this is all you need already for this week's assignment. If you want to make the lamp with the stacking layers or the environmental sensors with the modules, you put a little processor in each node. And as a reminder for the processors, don't forget our friend, the tiny 412. So the tiny 412 is a 15-cent 8-pin processor, and you can get these in even much tinier packages if you need it. Let's see. So in addition to the dip package we're using, oh, they're not showing pictures, but you can get it in a chip scale package that's even much smaller than this, but harder to solder. And so the nodes for this can be much simpler, much smaller processors than you might have been using. But you put the little processor in each module, and then you make one of these serial networks. Okay, so that's serial buses. Now we're going to do synchronous serial. And so the big difference between asynchronous and synchronous is in this, we're going to have a data line and we're going to have a separate clock line. So in asynchronous, there's just simply a line and you put data on it. In synchronous, you have a line where you put data on it. And then you separately have a line that says when the data is valid. And so somebody listening listens to the clock line, and the clock line tells them when to read the data line. With asynchronous, you need to agree on a fast on the data rate. With synchronous, and you need to always be listening to be sure to catch just the right moment. With synchronous, the clock line tells you when to read the data line. And so there's two common flavors, SPI and I2C. They each have a long history, but at this point, you can ignore the history and just use them. So SPI, a serial peripheral interface, you'll see many names for the lines. Historically, it had terms MISO and MOSI and SS, which were master in, slave out, slave in, slave select. And there's been an effort to purge language about slavery. So you'll see peripheral in, controller out, or serial data in, serial data out are terms you'll use for these lines. And so we're going to have 4 of them. One is data going out, one is data going in, one selects who you're talking to, and one is the clock. And so Arduino, MicroPython both have SPI libraries. Generally, you won't use SPI between 2 of your own processors. You'll use it when you talk to something that speaks it. And one of the great examples of what speaks it are memory cards. So here's an example of an RP2040 connected to a flash memory card. And then here's a video of, I reset the processor. I'm just going through the steps again here. I'm going to load MicroPython on it. Then I have to connect to the correct port now, which is moved. And then I need to tell MicroPython how to talk to memory cards. So I'm saving on the RP2040 the SD card library. And now I run this program, and what happened didn't look that exciting. But what I just did, well, now let me show you the code. Leo's asking why not SPI. So Leo, SPI needs 4 lines, and it's not really convenient for multi-drop. It's typically, a processor and a peripheral. It's not designed for a network of many things. You can have more than one thing, but you need the chip select line to pick them. So let's look at first the board and then the code. So on the board, I've got my lines that I'm using for the SPI data out, data in, the clock line. And just as an example, this is a board where I could have made a 2-sided board, but I couldn't route that from there. But when I'm milling a board, rather than sending it to a board house, if I just have one connection I can't do, rather than flipping it mill both sides, I'll just run a wire jumper. This is an example of that. And now let's look at the code. And this is beautifully simple, thanks to the wonders of the libraries here in MicroPython. So I read in the SD card library that I saved on the device. So I've got linked here, let's see, I don't have SD card. Let me make a note, link. I'll add a link to that, but if you just search for it, you'll find right away the routine. Okay, so if we go back to the Python code, this says I want to use my pins as an SPI port. Then this says I'm going to use the SPI port to talk to the memory card. Then that gives me access to store bits on it, but I actually want to store files. So this says I want to make a file system on the memory card. And then this finally, this is where MicroPython is essentially almost a complete operating system. This says I want to mount the file system so I can get it on the processor. So this is a stack of SPI to the card SPI to SD. Once I have SD, I need a file system. And then once I have a file system, I mount it. Then at that point, it's really easy. All I do is I write in, I open the file system and I write to it. And then here I'm going to list what's on the card. And then here I open the file system and read from it. And so that's all it takes. And so once you do all of that, you know, at the end, when I run it, it's not that exciting. But what you'll see is I wrote the file. Here it lists the file stored on it, and then I open the file and I read it out. And so the SD cards are cheap, you know, dollars depending on the size. This lets you add gigabytes of storage to your project. It's non-volatile. It stays without power. And it's surprisingly fast. You can talk to it in milliseconds. There's actually an even faster protocol beyond SPI you can use with these cards for even higher data rate, but it's much more complex to talk to. And so this gives you a surprisingly fast way to write and read large amounts of non-volatile data in your projects with an SPI interface. Now I've got two other examples. This example does it with D11. And it's fairly similar in using the Arduino libraries that know how to talk to an SD card. And then this last example is a borderline perverse one I did quite a while ago. This is using just a ATtiny, a very minimal processor. And what I'm doing is I stored Alice in Wonderland on the card, and I'm reading it from the card. But in this one, I did everything from scratch. I wanted to learn how to do it. So first of all, this is implementing SPI in software. And then this is the code to talk to the SD card. So this is how the SD card communicates. And then all of this stuff this is nasty. I don't recommend learning it. Is the SD file system. Oh, and I should stress the memory card has to be formatted with what's called a FAT file system, and that's the most common one. It's a sort of a bizarre, nasty old standard that dates back to Microsoft. And this part of the code wakes up the card. And then this part of the code is reading the FAT file system on the card. And then it's using it to find the data on it. So normally you don't need to know about that. Oh, that's hidden to you by the libraries. This is an explanation of the FAT file system. And let me make a note. When you buy the card, sometimes it's formatted, sometimes it's not. You need to use your computer operating system to format the card with a FAT file system, and then you can do all of this. Okay, so that's SPI with an example talking to SD cards. I2C had a slightly complex history of being proprietary, then fought over, and then there are different names for it. Now that's done. Here there are two lines. There's an SCL line and an SDA line. This is the clock line. This is the data line. But the crazy thing is they're shared between the processors. So the lines can go in either direction. And the way you do that is on each line, you have a pull-up resistor that pulls it high. And then the nodes can pull the lines low. And so they can share the line by, it gets pulled high, and then you pull it down to talk. So on this board, I've got the processor. I've got the pull-up lines on SCL and SDA, and I've got this connected to just a general purpose header. And oh, sorry, not that one, this one. And then what I'm going to do in this example is for Arduino, I2C is called wire. And so I'm going to start I2C, and then I'm just going to scan over the addresses. And there's standard is 127 addresses. And so in this example, I'll load the code. And then I start the port scanner, and it's saying, I don't see anything, I don't see anything. And then I'm going to plug in an I2C display, and now it says I'm finding the I2C display. So I2C lets you connect devices where each device needs the hard-coded address. So a bit like what I showed you in this first serial version. You need to have a fixed address, and many of the parts you buy for sensors or actuators speak I2C, and they have standard addresses built into them. And this is a link to Adrian, where he did a version of I2C between multiple devices. So you can use I2C between devices that come to you speaking I2C. And I2C is a convenient protocol to talk to your devices, where you do I2C on both sides, just with the note that you do need to pre-assign the addresses to them. So that's I2C, and emerging, but not yet widely supported, is I3C, which is meant to take the best of everything I just told you and synthesize it together. And so it's a coming attraction. It's not yet mature. Last thing I'm going to show you for wired is, yeah, there's a note from Ricardo about, and I don't really talk about this, long cables. When you have a long cable, there's a lot of capacitance and inductance, and it can take a long time to charge. And as the signal travels down it, you can get reflections. And so at high data rates, much more thought goes into how you drive them and how you terminate them. It's not an issue for sort of this size things in front of you. The last thing I want to show you is something I've used in some research projects. So this isn't a standard at all. This is something just I've used in some projects where I need it, which is all of the examples so far have a fixed data rate. And you have to decide in advance the data rate. And so one question is, where does that come from? And one question is, excuse me, if you have a very fast processor and a slow processor, how does the fast one talk to the slow one? So ATP is an asynchronous token protocol, and it's designed to work without clocks. So what you do is, excuse me, sorry, there's two lines in each direction. One line, so we're back to 4 wires. One wire is for the bit, is the bit low or high. And one, oh yeah, Hank is showing MPCM. And let's see, I believe only AVRs support that, but it's an AVR protocol. So what ATP does is there's a wire that says, is the signal low or high? And then the token line says, is it valid or not? So token 0 means a 0. Token 1 means a 1. 0, 0 means nothing's there. And 0, 1 means it's occupied without saying the value. And so the way you exchange data is the sending side says, I have a token, and puts up the data. The receiving side, by saying I'm occupied, says I've accepted your data. The sending side, by eliminating the token, says you've taken my data. And then the receiving line saying I'm empty says I've accepted it back from you. And so think about this like a checkers piece moving on a board. The data is like a token. I'm passing a data token to you. And so in this implementation for, I'm going to use a shell, and I'm connecting it to power, ground, and then the four signal lines. And so it lets me do a couple things. So I'll go over the code in a second. One thing is it lets me talk very quickly. So here's the data line, the token line, the bit line. And in this case, I'm running at, it's at 7 megahertz, 7 megabits a second. And I didn't pick 7 megabits a second. You just start it running. And the system picked that data rate because that's how long it took to do it. And then here's what's really neat about this. What I'm going to show here is this is the sender, this is the receiver, and this is a logic analyzer. And the sender is putting out a string. The receiver is reporting characters as it gets them. So if I start it going, the sender, you'll see it's saying I'm sending hello world, and here are the characters. But now watch what happens if I stop the receiver. I can stop the receiver in the middle of a transmission. And now what happened is the token line has gone high. The sender is saying, I've got data waiting for you. The receiver is just ignoring it. And then when I start the receiver again, it just picks up and where it left off and starts getting the data. Same thing if the sender goes away, and then just when it starts putting tokens, the receiver can see it. And so what this, if we go back here, is, let's see, what it's letting us do is exchange data without a clock. And you can, it's asynchronous. We can stop at any time and start up again. Now to implement it, remember the PIOs in the RP2040, these little processors. So the code is very simple. I just said I want to put a message. And in here, so let me go back to, this is the diagram of what the exchange looks like. And I won't take the time now to go through in detail, but this is what the PIO code looks like to do what I showed in that diagram. And so that's what the sender looks like. And this is what the receiver looks like. So this is an example of an unclocked protocol where instead of having to agree on a data rate, the system automatically figures it out. So two fast processors can talk very quickly, but if you want a fast processor to talk to a slow processor, they'll figure out what rate they can talk at. And you don't need to always be paying attention. You can always go away from the communication and do something else, come back, and you pick up where you left off. And that's because it has what's called a static state, that you don't need to know what came before. You can just reconnect at any time. So that's ATP for asynchronous communication. Finishing with wired, you've been using USB. Tiny USB is a really nice version of a USB library. And then for both Python and Arduino, these are libraries that let you talk directly to USB. And one of the exciting things you can do is you can be a HID, a human interface device. So you can make your device appear, for example, like a keyboard or a mouse or a joystick. You can make your device appear like a MIDI device. You can make it appear like a memory device. If you think about all the USB things you plug in that your computer recognizes, you don't need a library. There's libraries for both Arduino and Python that let your device have USB profiles. Ethernet is widely used for fast networks. If you need to talk to Ethernet, standard way to do it are these modules that convert between Ethernet and a processor. And then CAN, LIN, Modbus, DMX are commonly used in industrial automation, in cars, in light shows. I wouldn't pick them to start for one of your projects, but they're standard interfaces to them if you need to talk to that protocol. So that's wired networks. Yeah, Hank is noting CAN bus being used more and more in 3D printers. There's some propagating down. And one of the nice things about the PIOs is PIOs know how to speak just about all of these protocols because of the way they're reconfigurable. Let's go on to radios. So that's with wires. Nicholas, what are you saying about data rate?
Yeah, sorry, I'm having a camera issue.
Okay.
On the Tinies, there are some lean related actually peripheral that let you synchronize the UART data rate. So even with the simple RC oscillator and so on, you get good enough synchronization.
So yeah, the way I would
You can do Lin actually on the chip, but you are not obliged to use the Lin protocol. You can just use the Lin synchronization.
Yeah, so this is what's called timing recovery, which is if you have, for example, a not very accurate clock and you're not sure of the clock right, a more powerful processor can listen to the data, and from the data, it can figure out what data rate it's sending it. And so there is still a clock, but you can adaptively recover the clock. And then again, versus the asynchronous thing I showed doesn't even have a clock at all. Okay, radios. Now we're going to get rid of the wires. This is a wonderful, the ARRL handbook is a great book to have in your lab. That's everything you ever wanted to know about radios. These are the parts of a radio. An oscillator makes the radio signal. A mixer combines it with the message you want to send. PA is a power amplifier that sends it out. LNA is a low noise amplifier that receives it. IF is this intermediate frequency that processes the signal. I and Q has to do with how you modulate it, which I'll talk about in a little bit. Demodulation is where you separate the message from the radio carrier. Baseband is what you do. That's audio or the data you actually get. And then filters are part of pulling your signal out. To use radios, you need antennas. This is a surprisingly subtle topic. This is one of the Bibles on antennas. Antennas typically are tuned. So if you look at the frequency and you look at the amplitude, typically antennas have a center frequency. And if you send a signal, it's like pushing a swing. If you send a signal at that frequency, you get more signal out, and you don't see adjacent frequencies. Antenna gain is you can have an antenna that radiates in every direction, or you can have a directional antenna that sends more energy in one direction. That's a stronger signal. Impedance matching is there's again a surprisingly subtle subject of, we talked about long lines for wired networks. If you send a high frequency down a wire, when it gets to the end, it actually just gets reflected. For it to go off into space, you have to do what's called impedance matching. So the signal doesn't get reflected, but comes back, continues on. And that's a subtle RF circuit design. And so there's a lot to say about that we won't do in this class. Periodically, I teach a class on the physics of information technology. And in the notes for this, I talk about what's going on with impedance matching and transmission lines and antennas and radiation. Other than knowing that exists, we don't need to know about it here. The magic of what makes what we're going to talk about possible are single chip radios. And these are spectacular. So this is an example of a few dollar little single chip radio. And in here is everything I just said. So your data comes in. Part of the chip makes the radio wave. Your data gets modulated. It goes into the power amplifier to send out, and that's a strong signal. But what's coming back is a very low-level signal. So you need to separate the big signal from the little signal. Then you need to pull out your data, and then out comes the message. And so all of that's running in these single chip radios. Once upon a time, we used to use those from scratch, and we would build everything. Now you can get, thanks to really our friends in Shenzhen, these more complex chips that have the radio plus the protocol. And our favorite now, in fact, actually, let me make one note, is the ESP32 is one of our favorites. So the ESP32C3, which you can get in this Xiao module for $5, $4 in quantity, consists of a powerful processor. This is a connector for the antenna, and it has all of the radios on board. And so in particular, it has, at a frequency of 2.4 gigahertz, which is a common one, it knows how to do Wi-Fi and Bluetooth. So this is a very simple board where all I have on the board, and I've used it in other examples already, is a button, an external LED, and this comes with a connector that goes to the antenna. So let's do the examples. So there's a lot going on here. Here's my MicroPython. I need to load MicroPython on it. Then I'm going to put two packages on it, microdot and microdot async IO. And when we get to the code, I'll show you why I'm doing that. Okay, now the Wi-Fi radio here, it can connect to an existing access point and be a client, a station, or it can actually be an access point you connect to. So in this case, I'm going to make it an access point. So I start it running. When it started up, it has the address it's at. Now, this is my desktop computer. I've called my access point Fab. I'm going to connect to the access point in the radio. Now, when I'm connected to it on the USB port, it sent out the address that it's at. Now I'm going to go to a web browser. This is a web browser on the desktop. My computer is connected to the access point on the Xiao. And then from here, I'm going to turn the LED on and off. And then I'm going to push the button to do that locally. Okay, so in that example here, I start up the Wi-Fi radio. Then I'm going to start up a web server. Async IO lets me manage multiple tasks. So one task is listening to the radio, another task is listening to the button. So this creates a task for the button, this creates a task for the radio. My button task says when I push the button, light the light. And then my radio task says, when I get a message in, send the web page. And based on, if I get the root request, I send my web page. And if I get the web page, if I get a request on, turn the light on, off, turns the light off. And then this little bit, this is the HTML stored in the radio that I'm going to send to the client. And so all of that at the end lets me serve a web page from the SHAO and interact with it from a browser. Okay, second example is I'm going to use the very same board, but I'm going to do Bluetooth. And so there's a lot going here. So here I need to save the Bluetooth library. Then here I'm using a Bluetooth scanner. And so a number of the radio manufacturers make these apps for your phone that let you interface with Bluetooth devices. So I'm going to scan, and now I'm going to connect to my phone, my phone to the device. And now I'm using the phone to turn the LED on and off. And I'm pushing the button and getting a message on my phone. Next, I'm going to do it from a browser. So Chrome family does web serial. It also does web Bluetooth. Most other browsers don't support it. It's an experimental thing for safety and security. But if you turn it on, now from Chrome, I get a browser that lets me find my device. And now I'm turning the LED on and off, not with Wi-Fi, but with Bluetooth. And if I push the button, I get a message in the browser. So that's taking our $4 ESP32C3. And now I import the Bluetooth library. I start it up as a Bluetooth device. And then the code is really simple. That's all I have to do at that point. Now I'm talking to Bluetooth. And Bluetooth has many different profiles. You can be a heart rate sensor, you can be a speaker. This is using a particular Bluetooth profile, Blue Art, oh, it's actually linking back to me. So, oh, sorry, I forgot this is something I wrote, is why. But this is something I wrote based on these examples, but I combined them. This is implementing a UART. We talked about UARTs when we talked about sending and receiving messages over wires. This is implementing a UART over Bluetooth. So it's as if we have a wire going through space. You just put bytes in and bytes come out. And these are the full libraries that I based it on, but they were much more complex. What I wanted to do was take elements of all of them and simplify it. And so with that simplified version, all you have to do is say, I want a UART, and then you can talk to it. So that lets you make a Bluetooth connection where this is just between two devices, but it lets you send the equivalent as if you had a wire, but without a wire. And so this is great, for example, for remote controls, for phone interfaces into your devices. So all of that is on the ESP32C3. In the same family, there's an S3. There's now an S6. And the Pico W is, if you're using RP2040s, the RP2040 doesn't yet have a radio, but the Pico W is like the Pico with the RP2040, but with a separate chip that's the Bluetooth radio. And these are still very cheap. These are about $5 each. And so that's an easy way to do. And the very same code I showed you will run on those. And finally, the ESP32 CAM is a version of an ESP32 that can do Wi-Fi and has a camera. And you can do this with the shells with the sense. And so in this example, what I show is I'm going to run a demonstration program where this is video being streamed over the web from the ESP32. Okay, so that's ESP32s. The shells make it cheap and easy to talk to Wi-Fi. ESP8266 is an older processor. Let's see, let me go to, there's a standard module these come in, and these are just a few dollars each. So they're even in quantity cheaper than the shells, and they're just a minimal, it does just enough of, you can plug them into a project. In this version, I show web serving. And so it's serving a web page. In this version, I show it being an access point that you connect to. And so the shells generally are more convenient at this point, but the ESP01s are cheap. And if you just simply need to paste a Wi-Fi radio onto another project, they're an easy way to do it. Then next comes this is a standard module for RFID. So this is a kit where you get the board and you get a few tags for just a couple dollars. You should know this is completely insecure. I wouldn't use this for anything sensitive. It's very easy to hack the protocol. But the protocol is really simply, all I'm going to do is connect my processor to this SPI interface. And so let's do the video first. So I've got the RFID reader connected to my processor, and I'm going to just do a pre-made example. I have to tell it the pins I'm using. And then with the standard library, I start it running. Okay, so I brought the card in, and then all this data spewing out is the data stored on the card, which is, you can read and write the data. Then here I'm going to show, here's a smaller tag. But then what I'm going to show is you can open that up, and there's almost nothing in there. And so here's the chip, and then this coil is the radio. And so for the example of the tokens, the person I was talking to earlier, you can buy these chips, you can wind the coils, but the cheapest and easiest thing is if you just buy these tags, a couple dollars, you can peel all of this out and paste it into your project, whatever it is. You don't want a lot of metal right next to the antenna. Other than that, you can paste that in. And so this is reading the data in the tag. And so you can work with the chips directly, but these modules are so cheap and so convenient. I would just, it's easy to buy them in that form. And then this is a library that talks to the standard thing that implements the reading and writing and communication. So that's RFID. Then this family, these are programmable radios. And so these are popular, common. This is a single chip radio with the antenna on the board. This isn't Wi-Fi or Bluetooth. ISM refers to frequency bands that are available. This simply lets you send data between two of these. And so if all you want is like a car with a remote control, a simple way to do that is you put one of these on each side and it'll send a message between two of these radios. This is the same, sorry, not that one. This one is the same thing, but at a lower frequency. So if you want to do something like that, but you want to go at a longer distance, it's a lower wavelength. That higher ones are line of sight. As you start going down in frequency, the longer wave is more forgiving. So if you want to like send a message to and from a tag on a sheep in a field, these are convenient for lower frequency. And finally, LoRa is rapidly maturing. LoRa is kind of like Wi-Fi, but designed for multi-kilometer links for city-scale networks. This is an example of LoRa modules, LoRa boards. And so line of sight, Wi-Fi doesn't propagate long distances, has trouble with interfering objects. LoRa is good for long range signals and is maturing very quickly. Just a couple minutes left. Software radio is, the processors we're using are now so fast, the clocks are increasingly as fast as the radios. So you can implement radios in software. And I'll end with just, this is really a set of pointers. I won't take the time in detail, but when you network, these are the standard names for the layers, from the physics to who gets to talk, to how you route messages, to how you manage the communication. These are the rules for how you talk to networks, and the frequencies you can use are different in different parts of the world. Let's see, that's not loading. But this is a link to a table of many frequencies are reserved for commercial use, military use, government use, and some frequencies are available for you to use. Power is also tightly regulated. So these are the regulations on it. It's in different parts of the world. For wireless, you don't have to use radios. You can use light. And so old optical remotes used to do it. And these are more recent standards for sending high data rates by blinking lights. You can also use audio above acoustic frequencies. Then for time, I won't talk about it. This is how you modulate the signals. This is how you share channels. This is about the internet protocols. And so this is at a low level how you talk to the internet. There's a lot we could say about what's going on under the hood when you're actually talking to the internet. I won't, for time, I won't do that now. And then, yeah, Enterprise Fab Lab is asking where to get started. So to get started this week, if you know you want a wired network, for example, the environmental sensors, where we wanted to have a light sensor and a sound sensor and a gas sensor, I would start with a wired network. And depending on what you want to do, any of these are fine starting choices to implement a simple serial bus or hop count. If you know, wires are good if things aren't moving and you want to send power and data. If you know that you're talking to SPI or I2C devices, you can do that. If you're adventurous, you can play with unclocked protocols. But if you know you want to talk to Wi-Fi or Bluetooth, if you want to be a web server or a web client, or you want, for example, to go to your phone, I would start with the SHAO and go with that. And this week is a pretty easy week for the electronics. The boards aren't going to be at all complex. The libraries are very complex. Once you learn to use them, your code is fairly simple. Under the hood, there's a lot going on. So as a group, I want you to do a version of what that Japanese example did. Take two people's projects and send a message between two different people's projects. And then individually, I want you to design and build nodes. And the difference from before is when you just plug into USB, there's no address. You're just simply you connected to a host. I want you to do something that has addresses. And so it can be any of the different kinds of version, but you know, I2C, Wi-Fi, Bluetooth, hop count, all of those you can talk to more than one node at the same time. And so the crucial thing is they have addresses. And then I want you to have something local, some input or output, and go between something local to the node and something on a network. And so it can be between two processors. It can be between your node and the cloud, but I want you to pass messages. And you might do that because something's mobile and moving. You might do it because something's far away, or this whole project might be just within your final project, and it's an architectural way to make a modular system. By building a processor for each function, you can debug them separately, you can test them separately, and you can start assembling them to make a scalable modular system is a good thing to do this week. So that's an introduction to networking. Ricardo is noting work he's done on bit banging. And with that, always Saturday open time. For those of you who haven't been coming, you're missing out on great support. Education recitation picking up on Monday. And then this is the last hardware week. Week after that, we're going to be building application programs. Well, not quite. And then Wildcard is an open week. And then the remaining weeks are stepping back to look at context and diving in on final projects. So use your time, remaining time well. Do make a schedule between now and finishing, and think about how the networking assignment helps get you to the final project. Okay, happy networking. See you at the Monday recitation. Bye-bye.
Gracias, Neil.
Gracias. Sekarang akhirnya tak.
Thank you.
Bye bye.